But if you can't catch it, you can call me the same. I don't know. Yeah, I don't mind.
Well, ladies and gentlemen, thank you and thanks to the organizers for giving me the opportunity to talk about salt, one of the two major sources of caustic chlorine production: salt, water, and of course utilities, electricity. It all starts with salt. Salt was one of the first materials developed after the Big Bang and after hydrogen and helium and so on and so on. Chlorine, chlorate and sodium are the most stable ions, and they marry together and form salt. With the precipitation of water, the salt dissolved some 2 billion years ago and formed the seas. It evaporated, formed deposits of salt, and this salt is now found as salt deposits all around the world as rock salt underground. So what do we have? How is the quantity of the salt that we are actually getting out of the earth and producing for use? It's roughly around 300 million tons a year, and it is divided approximately equally between solar salt, rock salt, and brines. The chemical industry, that means the caustic chlorine production and the soda ash production, use approximately 60% of all the salt that is being produced worldwide. Yesterday, in the last presentation, we have seen the figure of 99 million tons of salt of caustic produced worldwide, so that requires about 150 million tons of salt, and the rest goes mainly in the soda ash production. Quality of salt, salt purities. There are some salts that are extremely impure, 50% perhaps, and then it goes into the very, very high purities, what I would call the ultra pure salt. The prices of these salt, of course, vary, and they can be as low as perhaps not even $10. Some of the cheapest sources of salt for caustic chlorine production are found in Texas, where Texas Brine is producing and supplying around 20 million tons of salt per annum for the caustic chlorine production, and this is done at a price of about $5 or $6 per ton of sodium chloride. Of course, it's liquid sodium chloride, so the utilization in membrane technology has to be suitably adjusted. It can be directly used for diaphragm production of caustic chlorine. Impurities in salt. We have heard in most of the presentations here that it's not really the sodium chloride in salt that is important. It is the impurity or anything else but sodium chloride that is important for the caustic chlorine production. They are all the same in all the salts that are produced worldwide. These are the main components of impurities, and they only vary in the quantities and in the concentrations in the sources of salt as they are being produced. Some 20, 30 years ago, we spoke about calcium, magnesium, and sometimes about sulfate. Nowadays, we spoke about approximately 30 components of the salt, and this is what we need to analyze, what we need to compare, what we need to take care of in the brine purification plants. Important impurities in brine for membrane cells. We have licensor A and licensor B. You all know who they are. And this is what they specify as the impurity, maximum impurity levels in the brine that is actually entering the cells, the membrane cells. Now, between the salt as it is being obtained somewhere in a mine or in the solar salt works and this final level of impurities, there are many production steps and many purification steps. The purification does not start after the saturator. It already takes place in several processing steps before the salt actually reaches the caustic chlorine plant. So, some of the basics. This is the basic chloralkali equation for chlorine. It's sodium chloride plus water plus electricity producing sodium hydroxide and chlorine and hydrogen. This is the main chloralkali equation for soda ash production. Sodium chloride plus calcium carbonate produces sodium carbonate and calcium chloride. What is the reason that the salt should be pure for these two basic production or chemical production processes? It's the membrane damage in membrane cells. This is what this symposium is about. Hydrogen evolution in mercury cells. This is still of concern because mercury cells are still being operated worldwide. Incrustation in soda ash production, contaminated effluents, bromine in chlorine for organic synthesis, etc. The brine purification systems. Brine purification is mainly based on the calcium and magnesium precipitation. The calcium with soda, with sodium carbonate, forms calcium carbonate as a crystal of calcite. Magnesium precipitation with, for example, with sodium hydroxide, forming magnesium hydroxide, which is an awful thing. It's when you catch cold and when you are cleaning your nose, that this is how magnesium hydroxide looks in the brine purification plant, and it blocks every filter. So it's a very nasty product, and the way to deal with it is to precipitate calcium carbonate together with magnesium hydroxide, and then it can settle quickly, and the rest can be reasonably filtered. Then we have the overdosing of reagents. Now this is a very important point. We have to overdose the soda at approximately 4 grams per liter, 0.4 gram per liter overdoses, and 0.15 gram per liter of caustic. The overdoses has to produce a pH value of about 10 or 11, and this is required to actually precipitate the impurities together. Now, when the quality of the salt coming into the brine purification plant is varying, if the calcium is sometimes 0.1%, sometimes 0.2%, and sometimes 0.01 also, it is very difficult to maintain the overdoses of the chemicals in such a way that even the peak will be precipitated. And this is a very important economic thing. The users of the salt may be paying more for a little bit better salt, but because they also are getting supplies of bad salt, they have to maintain the high overdoses for nothing, and this is not only waste of money, it is also problematic in the cells. If you have too much soda ash in the brine, and this then decomposes in the cell, then you have too much carbonate or carbon dioxide in the chlorine. Brine purification, sulfate removal, also sulfate needs to be controlled, and these are the options. Barium is one possibility, calcium chloride is another, and nanofiltration is nowadays being generally used for sulfate control. This is the solubility diagram of sodium sulfate in brine, depending on temperature. The normal concentration of sulfate. How do I get back? This way? Yes, this way. The normal concentration of sulfate, somewhere around 4, 5, 6 grams per liter, has to be concentrated in the nanofiltration, and that it takes place somewhere here at a temperature of about 20 degrees centigrade. You can get a high concentration of sodium sulfate, and this is then discharged as purge from the nanofiltration plant. We have examined economy of use of various salts, vacuum salts, sea salt, rock salt, and so on, in various brine purification processes, and these are the companies that we have either been advising or we have supplied equipment. In the old days, caustic chlorine plants based on mercury cells, in the 90s membrane cell plants, and salt purification plants, or examined some other aspects of their brine and salt, brine and caustic chlorine production. We are very thankful to these companies for giving us information about their operation and about their cost situation. Cost of salt and brine treatment. Of course, I cannot tell you who is having what costs, but these are the medium and the minimum and the maximum figures. You can see that as far as the cost of brine treatment and disposal of the contaminated sludge is concerned, the minimum costs are somewhere around $1.5 per ton of salt, and the maximum can be about 40 times higher, around $30 per ton of salt. On the other hand, the cost of salt and brine treatment and disposal can vary between some $10 per ton up to about $60 per ton for the best quality of salt. What does it mean? That means that some averages are insignificant. You have to take a look always at the specific situation. Relative brine treatment cost, there you can see the same differences, the same large, very large differences in the cost factors. Now, what I have spent my life with, and what we have concentrated on in my previous company, Krebs Swiss, and in my present company, Salt Partners, we have concentrated on purification of salt that would be a step before the dissolution of the salt in the saturators. We want to take a look at the salt. What are the properties of that salt, of that crystalline salt, and how can we actually remove the impurities from that solid salt? Because that process is substantially cheaper than anything else that then takes place in the brine. So, the standard, most simple way of washing salt is to take some brine or some water, mix it with the salt and separate it afterwards. And this is usually done on industrial scale in the centrifuge, and there is some water, and there is a purified salt, and there is some filtrate from the centrifuge. Now, what we have done as our great idea, we have taken the filtrate from the centrifuge, which of course always contains some fines. And we have added water into the filtrate vessel, dissolved the fines, and used this pure brine in a vessel or in a decanter above the centrifuge for countercurrent purification. And this we have then completed with hydraulic transport of the salt to the top of the hydroextractor, and the overflow from the elutriator is then distributed through a brine pump to the various points in the vessels to control other unit operations. These unit operations are elutriation. Elutriation is a countercurrent, relatively slow countercurrent flow of brine against falling crystals of salt and crystals or small particles of impurities. The next one is hydroclassification. This is the same process as you have in a sand filter when you are washing the filter with upflow, and that can separate the impurities by sizes. The final operation is hydroextraction. The salt is usually not a monocrystal. It has cavities and crevices, and given sufficient residence time, we can remove impurities from these crevices by diffusion. Of course, this only works if we are using pure brine, and at the top of the hydroextractor we have a mixture of sodium chloride, magnesium sulfate, and the extent of purification of the salt crystal is very high. This process does not work everywhere. For example, if the decanter is of this shape, then there is a rat hole being built in the middle of this decanter, and the salt flows out through the middle. Instead, flowing in a plug flow. This is a picture taken in a pilot plant where we have a downflow of salt, upflow of brine, and here you can see that when we inject black brine somewhere here, we get flow of this brine only upwards, and there is no brine leakage in downwards flow. So this is important to understand in the design of the hydroextractor. We have built several such plants. This is one that is using waste heat from cogeneration in heating ponds with purified brine. This is a purification plant. Here at the back are cavities and production of brine. The cavities are used for storage of natural gas, of methane. These are the compressors. And we are harvesting the salt from time to time and purifying the salt in this plant. We are achieving purities of substantially less than 1 ppm of calcium and magnesium and 50 ppm of sulfate in that salt. So this is an example what can be done without going for vacuum evaporated salt. If you know that, and if you compare it with figures like this, commercial vacuum salt product and hydrosol purified salt, you can see that the commercial, a good quality vacuum salt, for example, as far as the sulfate is concerned, we are somewhere around 100 ppm in a very, very good quality vacuum salt, and we can get down to about 29. Now this is the same salt. This is not what I'm showing you before. This is a commercial vacuum salt that we further purify in the hydrosol process. You can see that on the surface of those salt crystals is in this example, 118 of sulfate, and 29 of that is embedded in the salt crystals. The rest is on the surface. It can be removed. Another example, we have a salt with higher sulfate, with also much more sulfate on the surface. But if you compare the calcium in the previous example is less than 1 ppm. That means that brine purification plant prior to crystallization, is working very well. And in this one, where we have 6 or 6.5 calcium in those crystals, and we can only remove very little, there is 5.8 still embedded in the crystals, then that brine purification for that vacuum salt plant is not working very well. We have even other vacuum salts that have 211 ppm of calcium, and out of that 66 is inside the salt crystals. We have 800 ppm of sulfate, and we have still 220 ppm of sulfate embedded in the salt crystals. So, if somebody says vacuum salt, then it does not mean that that salt is very pure. Cost related to salt use in membrane chloralkali manufacture. That's what we have been talking about here. It's the salt storage and handling, salt dissolution, contaminated sludge disposal, purge concentration, ferrocyanide, silica, and so on. We have power consumption, hydrochloric acid consumption. We have membrane life and production loss of extra production capacity. That all is or can be due to impurities in salt. So we have carried out a comparative study with one of our clients, and these are the elements that we looked at. 300,000 tons per annum of chlorine, and we have looked at all the aspects of the brine purification plant that have to do with purity of salt. And these are the figures. We have compared the vacuum salt that I was showing you before, the vacuum salt A, these are the figures, and compared it with a very pure salt that is industrially possible to make. And these are the figures. These are all the elements that we looked at in terms of euro per annum and in comparative. And These are elements that are not needed with very pure salt on the right-hand side, or cost so and so much on the left-hand side. And then finally, we have compared the total and calculated back what could be the cost of the very high purity salt compared with some not so good salt. And you can see that with the less pure salt, you, let's say, it is 27 euro per ton of salt worth. With the very pure salt, you can pay 46 euro per ton to get the same economy, right? So the difference is 20 euro, and it's about 75%. This all has to do not with the brine purification in the caustic chlorine brine, but with the brine purification and salt handling in the salt plant. So 20 euro per ton is what can be obtained as an advantage with good quality salt. Conclusions. High purity salt makes primary brine purification redundant. You don't need it. You can go straight through filtration and through ion exchange. The pure salt anion removal systems are not required, because there's some natural purge and some losses that take care of the sulfate. With pure salt, the membrane life is up to 6 years is possible. We are being told by some caustic chlorine producers, up to 8 years actually. With pure salt, plant operating cost is reduced. Plant extra capacity is not required. Loss of production is avoided. High purity salt can be 75% more expensive compared to some standard, with the same resulting economy. And in each case we have to examine separately, because there are no, the averages are meaningless. Ladies and gentlemen, thank you very much for your attention. I have not seen anyone who would have fallen asleep, so why not turn your salt into gold? Thank you very much. We were looking for you at the reception yesterday. You didn't come to the reception?
No, I am traveling with my family, like I said, so in the evenings I'm
High value organic chemicals from natural gas and salt, and we supply the salt.